All right, so here are the examples. This obviously will work best if you have the examples with you in front of you and kind of going through these with me. I'm not going to do every example because there's just way too many of them, and it's not a matter of not wanting to, but there's a lot of repetition. Plus, it's also great for you guys to have a crack at some questions on your own. See if you're picking up the work as you're going. Also, really helpful if you after you've gone from this to move on to the checkpoints questions, at least as a series of questions that you can attempt on your own. So what have we got here? Example 1. I'm going to go through all of this first page because we're right at the very beginning, so I'll do more of the examples early on, and when they start to repeat, I'll start to skip questions. Okay, so the first one, if you can see it there, it should be pretty visible on screen. Given that big G, the universal gravitational constant, and little g is the magnitude of the acceleration due to gravity, which statement is true? So you go through, look at, the answer in this case is C, but you often get a lot out of why the other answers are not correct. Okay, so I like to go through those as well. A, the value of G, big G and little g depend on location. Well, in reality, only little g depends on location, because don't forget, to calculate little g, you'd have to go gm on r squared, which means that g depends heavily on location of where you're actually measuring the field strength. So little g depends greatly on where you are. So the values of g at big G and little g depend on location is not true. Only big G is universal. So A is wrong. B is wrong for much the same reason, just the other way around. The values of big G and little g are independent of location. Well, that's only true of big G, so nope. And D, option D is little g is the same everywhere in the universe, but big G is not, and that's the exact opposite of reality. So in this case it is C. Big G is the same everywhere in the universe, hence its name universal constant, and little g is not because it depends on location. So it's C in the first example, okay? Example 2. Which of these statements best describes the forces acting on a satellite in orbit around the Earth? Now, I specifically remember going through this in the lecture part of the video, so there's no way you guys don't know this one. If you look through, option A, although gravity has no effect, there is still an outward force. Like, absolutely none of that statement is true in any way, okay? It's just nonsense. The satellite is kept up by an outward force that balances the force due to gravity. Again, this is just making up physics. Again, the answer is actually C, so we'll go down to D. The effect of gravity is negligible. Just ask the moon, right? The satellite is kept in orbit by its momentum, and the net force on it is zero. Of course, as we know, Newton's first law states that objects moving in a circle have a sum of the forces of zero. Not really. No, that's not the law at all. That's just complete rubbish. Okay, so that's D. Okay, D's gone. C, gravity is the only force acting on the satellite, and this results in an inward acceleration, just like circular motion, as you guys have already studied. It's C, quite clearly. All right, let's go to example 3 of 80. Which of the following is correct about the forces acting during a rocket launch? Okay, so this one's pretty good. Can you actually, have I got it on screen? Yeah, there it is. Cool. Which of the following is correct about the forces acting during a rocket launch? A, equal and opposite forces act on the rocket. This enables it to continue to accelerate even in the vacuum of space. I just don't know where to begin with how messed up that is. Equal and opposite forces act on the rocket. No, that's just not it. Okay, the engines exert an upward thrust on the rocket. So the engines are exerting an upward thrust on the rocket. This thrust exceeds the downward force of the engines on the air. So obviously that means that once it gets into the vacuum of space, they don't work anymore. We know that's not true. There's another C here, okay? So C is the correct answer, but again, we'll skip down D. The expelled gases exert a force against the launch pad. The launch pad then exerts an equal and opposite force on the rocket, causing it to accelerate. So obviously this is why rockets go up, because they're constantly feeling the launch pad below them, no matter how far up they are. Again, nonsense. Have a look at C. The rocket engines exert a downward force on the gases being expelled. These gases exert an upward force on the engines. This is the only one that is actually can even possibly rings true, as in it refers to the rocket engines operating sort of independently of anything around it. It's not pushing on the launch pad, it's not pushing on the planet, it's not doing some other weird thing. It is the gases being expelled and they're pushing back on the rocket. So that is true wherever the rocket fires. So that is the only possible answer for that question there. Okay, example 5. A satellite orbits Earth as shown. Which diagram correctly shows the direction of the satellite's acceleration? As described in, you can even see in this case that we have an elliptical orbit shown. Okay, even with an elliptical orbit, you can still see there is no reason for the arrow to point in any direction other than toward the center of the Earth. Okay, that is the only unbalanced force. It is the only force that is causing the satellite to move in an arc. If force wasn't there, the satellite would follow Newton's first law and progress in a straight line. So, wrong, wrong, wrong. It's the only one that is possible. Okay, example 5. All right, example 6. Example 6 is interesting because it makes use of a part of a formula that is not part of the study design, but is incredibly common. You would have probably experienced this as part of year 11 physics. Okay, a pendulum can be used to determine the acceleration due to gravity using the relationship T, so T for period, is equal to 2 pi root L on G, where L is the length of the pendulum and G is just the force of gravity, acceleration due to gravity at the Earth's surface. So where T is the period, L is the length, it goes on to say the acceleration due to gravity at the surface of Mars, and we're using this here on Mars, is less than that on Earth. So we're imagining a pendulum swinging at the surface of the Earth and one swinging at the surface of Mars. Which graph relates the variables for the pendulum correctly for both planets? All right, so you have to have a look at this formula. You can't just look at the formula and guess. You need to do a little bit of work on it. Okay, so what I'm going to do here is I'm going to try and get this formula organized so that it puts L in terms of T. See here you've got the vertical axis L for length and the period for T down here. All right, and so traditionally, if you imagine this as a sort of a XY graph, you would often have these graphs expressed, a formula expressed as y in terms of x. And in this case, we've got L in terms of t. So if we could express this as L in terms of t, this relationship, L in terms of t, it might give you a better chance at seeing which one of these graphs is the most appropriate. So we start by basically squaring both sides of this equation, giving us 4 pi squared L over G. All right, and now we don't really need to rearrange too much, but what we will find is if we multiply things out to get this in as L in terms of T, you end up with this relationship here. L is equal to T squared G over 4 pi squared. Now, at the surface of any planet, what you're really looking at here, hopefully you can see this, what you're really looking at here is that this whole part here, G for Mars, will be a specific value at the surface of Mars. 4 and pi squared, again, are specific values. So what you've really got here is L is proportional to t squared. Okay, so L is proportional to t squared multiplied by some constant here, which is specific to both Mars and Earth, all right? So you know from any kind of mathematical study that you've done to this point that if L is proportional to t squared, what you're looking at here is a quadratic, as a sort of it's a curve, as you can see. This is not linear, it has to involve a curve. So that basically knocks out both A and B, okay? Because they describe linear relationships between L and T, okay? So length and period, okay? So which one's the correct one? Is it C or D? Does the period, is the period shorter as the length extends, or is it longer? As you can see here, G, so if we look at this here more clearly, when we're looking at L is equal to t squared multiplied by G over 4 pi squared, this G here, if this number is bigger, as it is on Earth, and I don't know how much you know about the planets, but Earth is significantly bigger than Mars is. In reality, Earth and Venus are much closer when it comes to being sister planets than Earth and Mars, just that Venus is so damned hostile that it's completely useless to even try to do anything with, whereas Mars is a little bit nicer. So G on Mars, on Earth, is much bigger than it is G on Earth is much bigger than it is on Mars, and hence, so if G is bigger, then it basically means that L is bigger for, or L gets longer as T gets bigger for Earth. This puts Earth above Mars when it comes to how these curves shift, okay? So a bigger factor here, if you know your quadratics, a bigger number here means a sharper incline here. Just like if you were looking at, like, can you actually see that? Just like if you were looking at like a y equals x squared graph, if the bigger this number, the bigger the coefficient number is, say for example 2x or y equals 10x squared, the sharper the climb is. And given if G here in the position of the numerator is bigger and bigger and bigger, it means that it would climb faster and faster, putting Earth above Mars. Okay, hope that was clearer than it sounded to me in my head, but yeah. Cool. Let's see, what else have we got here? All right, this is the next example. This is example 7. When people went to the moon in Apollo 11, the spacecraft was initially placed in a parking orbit 190 kilometers above Earth's surface. This is shown below. They do love using the whole kilometers thing. Hopefully you're learning that, through experience, that when you read 190 kilometers, you're thinking, oh, 190,000 meters. Okay, hopefully that's what you're thinking, because that's what I'm thinking. All right. And also the other, another word that should be like sticking in your brain, like a piece of broken glass, is placing the target above the Earth's surface. This is another way of saying altitude, okay? So this is 190,000 meters above the ground, okay? So just looking ahead at the question, just sort of trying to be ready for whatever they might ask you, that you need to remember that the radius of the Earth has not been included in that parking orbit value that they've given you. But anyway, let's move on and see what the question actually wants, right? Which one of the following statements, A to D, best describes the origin of the centripetal force required to keep Apollo 11 in its circular parking orbit? A, Apollo 11's acceleration towards the Earth. Okay. Let's see, sometimes an option sounds kind of good, but you want to actually keep on reading and make sure that there is a proper, there may be a better version, okay? So look at option B, the rocket motors of Apollo 11. Well, you know, once you're in orbit, your motors are not firing. I don't know how much about space you know, but yeah. The speed of Apollo 11 in its orbit, so the speed of Apollo 11 in its orbit is what is the origin of its centripetal force. And let's read D. The gravitational field of Earth acting on Apollo 11. Well, yeah, that's got to be it. It is the gravity field, or acting on Apollo 11 that keeps it in its circle, just like the same gravity field that keeps the moon in orbit around the Earth. Okay, so it's got to be a D. Right. Oops. Okay, example 8. Which of the following graphs, A to F, best represents the net gravitational force acting on Apollo 11 as it travels from its parking orbit to the moon? Okay, so you've got to think here that the gravitational force, the net gravitational force, you've got to imagine that when Apollo 11 left the Earth, traveled toward the moon, it spent most of its time being decelerated by the Earth's gravity. And then only when it got really, really close to the moon did it start to sort of accelerate back, toward the moon again. Okay, and that's because the moon is so much smaller than the Earth. So, firstly, we're going to ignore any sort of linear relationship, since we know that the force of gravity is inverse squared relationship, so it's got to be curvy. That's wrong, and that's wrong, and that's wrong. And so it leaves us with these three curves over here. Now, looking at D specifically, you can see that halfway between the Earth and the Moon, basically the force of attraction of the Earth has been overpowered by the Moon, and now it's sort of accelerating towards the Moon. That clearly would not happen halfway to the Moon. The Earth is that much bigger. You would expect this to happen a lot closer to the Moon. Again, sort of almost the same reason here, so that's out. Over here, this doesn't really, again, this intersection here is very close to the middle again, all right? So it does show a much stronger effect from the Earth and a much weaker effect from the Moon, but again, that transition from when the Moon has control of Apollo 11 or anything else that's going that way wouldn't occur at the midpoint between. It would occur really, really close to the Moon itself. Okay, that's got to be C in this case, okay? That's the one. That's wrong as well, okay? Alright, so let's have a look at example 9. NATO 3 is a communications satellite that has a mass of 310 kilograms and orbits the Earth at a constant speed at a radius of 4.2 by 10 to the 7 meters from the center of the Earth. That's an important value there. Which one of the following statements, so again, in multiple choice, it tells you it has to tell you what it's looking for. Are you looking at more than one answer? This one clearly states which one of the following statements about NATO 3 is correct. Okay, so let's look at A. The net force acting on NATO 3 is 0, and therefore it does not accelerate. This flies in the face of everything to do with circular motion. NATO 3 would not be in a circular orbit if it had a 0 force acting on it. It'd just be going in a straight line. Okay, if we look at B, the speed is constant and therefore the net force acting on NATO 3 is 0. Again, that's just a mismatch of ideas. The net force is not 0. If it was, it would not be going in a circle. Let's skip down to D for, again, no reason at all. There is a net force acting on NATO 3, but it has 0 acceleration. how can you have a net force and zero acceleration? They're just contradictory. No, it's got to be C even without reading it, because the other ones are just so damn wrong. There is a net force acting on 803, and therefore it is accelerating. Just because it's not speeding up or slowing down or getting closer to the Earth doesn't mean it's not accelerating. Acceleration is just due to a changing velocity, and that is definitely happening. Okay, let's have a look at example 10. A severe strain on the credulity. Okay. As a method of sending a missile to the highest parts of the Earth's atmosphere, Professor Goddard's rocket is a practicable and therefore promising device. Now, this is a story about Goddard, who's one of the first people to invent and launch liquid-powered or liquid-fueled rockets, and right in the very, very beginning, some famous photos of him doing so. It is when one considers the multiple charge rocket as a means of traveling to the moon that one begins to doubt. For after the rocket quits our air and really starts on its longer journey, its flight would be neither accelerated nor maintained by the explosion of charges it then might have left. So in other words, once it leaves the atmosphere, I think what they're alluding to here is that they're not, it's got nothing to push against once it's out of the atmosphere. Okay, that the professor does not, know the relation of action to reaction, and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. It's like, wow, this is not very nice at all. And obviously, whoever this journalist was is much better positioned to criticize, as they obviously know. So which one of the following statements offers the best reply to the central argument put forward in the editorial? That once you leave the atmosphere, there's nothing to push on, the action-reaction doesn't actually hold. Let's have a look at some of these responses. A, the action-reaction principle does not apply in the absence of gravity, says who? Recent satellite data shows that space is not completely empty. There are always hydrogen atoms, protons, electrons, and other ions in so-called space. So they're saying that you're going to be pushing, your gases are pushing on that. Again, we don't need those to push against. Remember, it is the gas that's escaping from the rocket or from the engine, and that is the action. The reaction is the rocket propels away from it. Does not need anything, a launch pad, gas or atmosphere or anything else to push against. It works no matter what. So let's have a look at D. Rockets obtain all their required energy before leaving the Earth's atmosphere. Then when they are weightless out in space, they continue to move at a constant velocity. There's just so much wrong with that. Okay, it just means that once you're in space, there'd be no way to move around at all, which obviously isn't true. E, although it is easier for the rocket to accelerate while it is in the Earth's atmosphere, wait, is it? So the rockets don't almost get ripped apart by being pushed against the atmosphere on their way up? That as soon as they leave the atmosphere, they accelerate ridiculously quickly up to their parking orbits? No, this quite literally states the exact opposite of what's going on. Like, I'm not even going to give it show it the dignity to finish reading it, okay? Because that's just rubbish. C, let's go back to C. Rockets do push against something, their own exhaust gases. There it is. It's got to be C. All right, lovely. Okay, so what's next? Example 11. Can you see that? Yeah, it looks like you can. All right. An object is let fall from rest at point X, right there, 6,400 kilometers above the surface of the Earth. All right, so in other words, 6,400,000 meters above the surface of the Earth. So you can see here that it's at 2 Earth radii away from the center of Earth. Which one of the following graphs best represents the strength of the gravitational field as a function of distance from the center of the Earth? Okay, now there is only one graph As you can see, this is an old question. That's 10. So this is gravitational field strength on this axis. That's 10 right there. So this implies that at 6,400 kilometers from the center of the Earth, you would have a gravity field strength, or gravitational acceleration of 10, or roughly 9.8. Okay, so that is the strongest gravity is going to ever feel at any position around the Earth, whether it's in the middle of the Earth or inside the Earth or above the Earth. That is the strongest of gravity that you're going to get. And we know because it's inverse squared law, which has been stated multiple times already, the only graph that follows that without doing any calculations, completely unnecessary, is this one right here. D. Only D possibly fits the model that we know exists. All right, let's have a look at example 12. A 60 kilogram object has a weight of 240 newtons on the surface of planet X. What is the acceleration due to gravity on the surface of planet X? Okay, so what we're looking for here, you need to recognize a couple of things. The weight force is a force, okay? So sometimes we call it W. Wait, can you see that? Oh, and I gotta move it in here. All right, there you go. That's better. Okay, so the weight force, or is this, force is the same as weight force, which is always equal to mass multiplied by acceleration, or gravity in this case, because we're talking about gravity. All right, so this 60 kilogram object has a weight of 240 newtons. What is the acceleration due to gravity on this planet? So if we just clean this up a bit and call it W equals mg, then we can see that we know the weight force is 240 newtons, which has got to be equal to the mass of this object multiplied by the gravity on planet X. So planet X, I have a very quick solve here. G will equal 240 over 60. Cancel a couple of zeros, and you've got 24 over 6. So gravity on planet X is 4 meters per second squared. Option B, a really, really simple calculation. The only thing about this question that is important is you understand when they give you a weight force that the weight force is a result or the product of the mass and acceleration of that particular planet. Okay, awesome. Okay, what's next? Is there anything worth doing in here? Oh, this is easy, too easy. I think I'd be insulting you too much if I tried to get that. Tried to go through examples 13 and 14. They just seem a little, they're just repeats of what we've already done. Okay. All right, this is an interesting question, okay? Over here, we're going to look at question 15, okay? So, can you see that there? Question 15, you should have it in front of you anyway. Let's see if I can zoom in a little bit so perhaps you can see it a bit better. So here it says, a satellite in circular orbit at a distance r from the center of Earth has an orbital velocity v. If the distance was increased to 2r, what would be the satellite's orbital velocity? In other words, how fast would the velocity, or what is the velocity of this object if you doubled the distance that it was? And I don't know if this is clear, but the speed of an object in orbit depends on how far out it is. So if you imagine a weight on a rubber band, okay, you cannot, if you spin the weight at a certain speed, okay, you spin this weight at a certain speed in a circle, and you'll notice, make it a horizontal circle, so we don't have any gravity to do with it, okay? So you spin this, and what will happen is, if you spin it at a certain speed, it's going to form a circle where the force required to keep it in a circle balances out the force that the rubber band is able to provide, okay? So you set a circle, okay? Now imagine you spin this mass faster, okay? If you spin it faster, what will happen is it will pull on the rubber band, and it'll take more effort for the rubber band to hold it in place, so the rubber band will stretch out, okay? Orbit works like that. So if you speed up in orbit, you don't keep the same orbit. What happens is you push out, okay? So if you want to climb to a very, very high orbit, you just need to speed up, okay? The more you speed up, the further out you'll sit. And so yes, for spaceships to come home, they don't aim at the planet and fire their rockets. What they do is they aim in the opposite direction that they're traveling in, give off a blast of hot gases, and slow down. As they slow down, their orbit decays. They get closer and closer. At some point, they start to slam into the atmosphere, and then that really takes the energy out of their motion, and then it becomes a whole other thing where they come crashing down to Earth. Well, hopefully, safely. Okay, so what we're getting at here is this question is about the relationship between the orbital velocity and the distance that the object is away from the center of the gravity mass, in this case Earth. So what we have here is we need to link orbital mathematics to circular motion mathematics. Okay, so these two, if we bring a separate piece of paper over here, you'll notice that this really becomes a question of F equals ma. All right, so hopefully you can see that. Yeah, it looks like you can. F equals ma. Now, there are two different forms of F equals ma, as we've already shown and discussed earlier. So we've got one version of F equals ma. F equals gravitational constant, big M, little m, big M being the planet Earth, little m being the mass of the satellite, divided by r squared, the distance from the center of the Earth that the satellite is sitting at. Now, we also have another version. So this brings our orbital sort of mechanics into it. Whereas, now we need to link the velocity, and the only way we can really do that is taking the F equals mv squared on r that we get from circular motion. Now, this r I'm using capital R because it's the r which is the distance to the center of the planet, and that is little m. Okay, so I'm going to make that bold, as you can see, and that's bold. Okay, so little m. This is the mass of the object, the satellite. That's the mass of the satellite. That's the mass of the planet. Okay, so now they're both equal to F, and they're going to both equal to F where we need them at the same R. So we're going to equate these. Okay, so to equate them, you just get G, big M, little m over R squared is equal to M V squared on R. Now this links our radii to the velocity. Okay, and with a little bit of mucking around here algebraically, we can actually solve for v to see what happens to velocity when we start messing with the radius of orbit. Okay, so we're going to cancel out the little m's because you divide them both out, they're gone. I'm going to multiply big R to both sides over here. That's going to cancel these guys out and one of those. All right, and that leaves us with G big M on R is equal to V squared. All right, so V squared is equal to the square root of GM on R. Okay, so you can see, oh, sorry, get rid of that. I square rooted it. There's no point of having a square there. Okay, so V is equal to the square root of GM on R. Now it's going to take a little bit of imagination to see what this actually means. All right, so let's take the situation as proposed, and that is that we double the radius of an object. How does that affect the orbital velocity? So let's take the velocity, and now we're going to double R. And we do it just by chucking a 2 on the R. So we've doubled R. Now you can see that G being the gravitational constant, the mass of the satellite didn't matter, hence it cancels out very early. The mass of the planet is the same in both situations, so original R and then double R. So what I'm getting at is gm and original r are basically constants. Okay, so by doubling r, you can see that v varies with the inverse of the square root of r. So the r is the only thing that actually changes. So when we double it, you are, by doubling the radius, you are dividing v by the square root of 2. See, that's where the square root of 2 comes in. So you end up as, by doubling r, so double r, you divide v by 1 on root 2. Okay, so 1 on root 2, 1 on root 2 is roughly 0.7, which is what makes the correct answer here. Okay, so this, I know this really relies on you having a really good handle on your algebra and sort of understanding how these relationships work. And again, none of that really happens unless you've done, I guess, heaps of work. All right, so that's the basic explanation on why that happens. Okay, so get rid of all of that, and let's see what's next. Okay, example 17, a satellite is moving in a circular orbit of radius. So given us r around the Earth, it has a speed given, 8.1 by 10 to the 3 meters per second. What is its centripetal acceleration? So this is a straight out circular motion question. It's moving at a certain radius with a certain velocity or a certain speed. Acceleration is equal to v squared on r. All right, straight out of circular motion. So you apply this, just being very, very careful. A satellite is moving in a circular orbit of radius 7 by 10 to the 6. All right, example 16. Just here. Okay, the gravitational attraction between two bodies is given by the equation below. G is the universal gravitational constant. M is the mass of one of the bodies, little m is the mass of the other, and D, in this case, rather than R, is the distance between their two centers of mass. So they're basically stating F equals GMM on D squared. And then they go on to ask, what would be the effect, or see, if the both bodies increase their mass by a factor of 2, both bodies, by a factor of 2, and their separation is increased by a factor of 2, by what factor would the original gravitational force be multiplied to describe the new gravitational force between them? This is a very simple question. It just asks you to go through and change the masses, so that becomes G. It says double both, 2 of big M and 2 of little m, and then doubling the distance or the separation. You just have to be careful that when you double the distance, that this is a squared relationship. So when you double that, you end up squaring. You end up squaring it. So you end up here with F is equal to 2 times 2 is 4, and I'll bring that out to the front, GM M on, and now you square this, becomes 4D squared. So you end up with 4 over 4, okay? So by doubling the mass of both objects and doubling the distance that they're separated by, you see that the force changes by a factor of 4 over 4, which is 1. It doesn't change at all. Okay, nice and easy, that one. All right, let's have a look at example 21. A satellite orbits Earth with a period t. An identical satellite orbits the planet Xerus, which has a mass 4 times that of Earth. Both satellites have the same orbital radius. So what is the period of the satellite orbiting Ceres? Now, this question, it links, what it's doing is basically a Kepler's law question. Okay, so this is linking sort of orbital mechanics to the rate of orbit of a particular object around a particular planet. It's an interesting treatment of Kepler's law because it's comparing two different planets, okay, and see how does the period change if the radius is the same. So you could go straight to your help sheet, which has this formula on it. G big M on 4 pi squared is equal to r cubed over t squared. So what we're going to do here is we're going to see how changing the radius, changing the mass of the central body while keeping the radius the same alters the period. So to do that, you need to do a little bit of rearranging and solve for t. So solving for t will give us this arrangement. T squared is equal to 4 pi squared r cubed over gm. And then obviously t will equal the square root of all of that. 4 pi squared r cubed over gm. Now it's big M. So what's important to notice here is, yes, you can square root that 4 and bring it out, but it tends to, I feel it kind of complicates things. Right now, this is the period, that is calculated by using these values. So 4 and pi squared are constant values, so is g. And in this case, r is constant because we've said in the question that we're putting both of these satellites at the same r. So that would mean that the period will be different because the masses are so different. So to compare what actually happens to the period, if we leave this arrangement exactly as it is and then rewrite it, so this is what it would be like, say, for Earth, which just has a mass m, as you can see there, and to compare that now to Ceres, which has a mass 4m, if we rewrite this equation as 4 pi squared r cubed over g 4m, okay, now to make the comparison the same, what you don't want to do is cancel out these 4's, okay, because it just makes the result harder to see. So you've noticed, what you should notice is that, okay, because the 4m is underneath this big surd here, let's see what its actual effect is on what the original equation was. And so to do that, you do actually square root this 4 as it is underneath the surd to see, because that is the only thing that is actually different here. So I'll square root the 4 and bring it out. So the period ends up, if I square root the 4, which is in the denominator, it needs to stay in the denominator, but as it comes out of the surd, it becomes square root, which square root 4 is 2, and that leaves now everything else inside the surd unchanged. Now, if the original period was based on these values, then the altered period is based on the same values, with the difference in that the period has been halved. So what this means is that you've got 4 times the mass would mean to keep this object in the same orbit, it would be orbiting at half the rate that it would be around Earth. So as t is the same as the square root of 4 pi squared r cubed over gm, the new orbital period is a half of that, okay, which is why it leaves us with B, okay? All right, that's a nice question. All right, I've just been scanning through, sort of come up to another question which may be a little bit more interesting, I guess. A lot of these you can follow quite easily with the, through the solutions. Okay, let's have a look at this one, just because it's got a little bit of an odd sort of twist on it. For satellites in a circular orbit around a celestial body, The period is related to the radius of orbit by Kepler's third law. T squared equals kr cubed, where k is a constant. Now, that's an interesting way of putting Kepler's law, because if you look at this, what they're really saying here is, let's say T squared is equal to k cubed. Okay, you can see that that's what they've said. Now, the way we often see Kepler's law is either it's going to be t squared over r cubed or r cubed over t squared. It doesn't really matter, it just depends on how you flipped it. But if we look at it like the way we traditionally look at it, in this arrangement, what they're basically saying that is if we now flipped this over into the way we have it written down on our help sheets, that's what we're looking at. So r cubed over t squared is equal to 1 over k from whatever this arrangement is. And it's pretty safe to say that, that if we then compare this arrangement to r cubed over t squared is equal to gm on 4 pi squared, which is straight off your help sheet, you can see that that 1 over k would be the reciprocal of this arrangement here. So what they're saying now, you remember, this is a constant for a particular body out there, okay? So if you started with this, okay, if you started with this, looking at this question, and then rearrange it to put it in the form of t squared equals kr cubed, so then get down to the point where you could say what k actually was, you can see that this is closely related to this, okay? Which means that, that is exactly the same thing. So to get it back up to the way they want it, you'd have to flip the whole thing over. So t squared over r cubed is equal to 4 pi squared over gm. And you can see, to get it into the form as stated in the original question, by simply moving that r cubed up, you'd get it in the form of t squared equals kr cubed, meaning that the k part of this is 4 pi squared over gm. All right, so 4 pi squared over gm, which matches up neatly to this, okay, to option E. Okay, so that's basically it. I mean, you can just pull that question apart now that you can see where I started and how I sort of finished it. You can mull over it in your own head and see if you can make it make even more sense. All right, example 29 though, which of the following statements about K is correct? A, it would have a certain value for Earth and one particular satellite, but a different value for Earth and another satellite, which is completely nonsense. That is, this question is about the statement of what Kepler's law actually is, and as we know, Kepler's law does not, orbits of objects in space do not rely on the mass of the particular object in orbit. For example, if you imagine seeing a spacewalk, for example, you would have seen footage of a space shuttle traveling around in a circle around the Earth, being in orbit, and you will have seen footage of people doing extravehicular activity. So some person in a spacesuit who is outside of the shuttle, they're both traveling at something like, 25,000 kilometers a second, and they're moving at a really, really fast rate in orbit around the planet. So if your orbital velocity or your period was different based on your mass, as soon as an astronaut left the space shuttle, they would end up either shooting ahead or falling behind, depending on whatever this difference was. And of course that doesn't happen. You can sit outside your space shuttle quite happily, traveling along at exactly the same speed as you were going when you were inside the space shuttle. So what I'm getting at is, for this option A to be correct, it would just make spacewalk completely impossible, which, as we know, is not. Okay, so whether you're a 5,000 kilogram satellite or a 70 kilogram astronaut, it's not going to change. Kepler's law is not going to change how you move around the planet. Okay, so A is completely out. If you look at C, it is like G, a universal constant. So, K is like G, which of course is not true. It is only a constant for that particular body or any body that has that particular mass. And if the mass changes, then the K, Kepler's K there would be different. Okay, so C is completely wrong. D, it is like pi, a dimensionless universal, again, no. It is not. It's got to be B. It would have a certain value for all satellites of the Earth, but a different value for all satellites of the Sun. It's the only one that is completely correct. Okay. If you look at example 30, the period of a satellite placed in orbit halfway between the Earth and the Moon would be, now this question's interesting because it assumes a bit of prior knowledge. If you don't know that the period of the orbit of the Moon is about a month, okay, so the period of is about 29 days. So you can see that the period of orbit of the Moon is about 29 days. So you know what the period of the Moon is, and it's asking, can you figure out what the period of a satellite halfway between the Moon and the Earth would be? Okay, so it seems like there's precious little information to go on for this question, but it's actually quite easy in reality. So if we start with Kepler's law, we're going to compare the satellite's period and radius with the Moon's period and radius. Let's say call this r cubed m for the Moon over t squared m for the period of the Moon has to be the same as r cubed for the Earth, for the satellite, not the Earth, for the satellite, over t squared of the satellite. So I got my little s's there. Can you see that? I think you can now. All right, sorry about that. Okay, now what we're doing here, so there is the radius of orbit of the satellite. So what we're doing now is we're going to halve that because it is halfway in between the Moon. So the Moon's orbit is essentially 1r and the satellite's is a half r, but we're going to have to cube that, okay? All right, so you can see that. Now we also know that the period of the Moon has to be about a month, and the closest value to a month I've got here is about 29 days. Now, it doesn't specifically say that it's 29 days, but it's a pretty foregone conclusion here that the reason 29 days is offered as an option is because they want to know, do you think that the period of any object around the Earth is going to be 29 days? When obviously it wouldn't be. So rewriting this gives us r cubed of the Moon, which is 1r, over 29 squared for the period of the Moon around the Earth has to be the same as r on 2 cubed over the period of the satellite squared. Okay, so now it's a little bit of fractions and algebra, and I know everybody loves fractions. I know I do. So you've got r cubed over 29 squared is equal to r cubed over 8t squared. Okay, if you don't know how that turns into that, you really should have focused on your fractions. All right, now we're going to solve for t because that's what we want to know. We want to show that what the calculation for the period of this satellite that is halfway between the Earth and the Moon is. So I'm going to now solve for t. So I've got now t squared is equal to, I'm going to bring t squared up there. I'm going to have r cubed here. I'm going to divide by this r cubed over here. And I don't need to denote e or the moon or the satellite anymore, because I've dealt with those values by putting the halves in and the 29 in and all that. So I'm going to now multiply this up here by 29 squared. That's the 8 is already there. I've brought my t squared up. So let's just check my work. Beautiful. Oh, and that r cubed is going to come down here and cancel out with the r cubed that's already there. Cancel, cancel. And I'm now left with a very nice, neat value. T squared is equal to 29 squared divided by 8. And so t will equal this, whatever that works out to be, which is about 10.3 days. Notice something else. I know I go to great pains to explain that we don't use days and we don't use weeks and hours or anything in physics, but because you can see in this question doesn't really rely on any other values, okay? So there's no masses in here, there are no velocities that are in meters per second or kilogram, there's nothing else to complicate it. So I've got only two variables in here: radius, which is in this case in terms of r, so 1r, half r, all right? And the other one is in days. Now, as you can see, if I put the values in days, they will come out in days. I do not need to freak out and go, oh, well, everything in physics is in seconds, I'm going to have to convert these days into seconds. You don't need to do that, because it's really not going to matter in this respect. Okay, so what's next? We've got this one here. I'm not going to bother with example 31. It's another direct application of Kepler's law as per the very last question that we just did. Looking at B, a satellite is orbiting a planet at a constant speed. Okay, now remember there's a distinction between the words speed and and velocity. If you're in a circle, you are not in a constant. You do not have a constant velocity, and a constantly changing velocity, which is why you have your acceleration towards the center. Okay, so just bring your attention to that. Okay, which of the following statements is correct? All right, so let's look at it and go, the satellite is not accelerating is clearly not correct. Okay, so they've used the word speed to try and suck you into thinking that the whole thing's not accelerating. It's moving in a circle, so it is accelerating. Skip B, go down to C. Fuel must be used to supply a constant thrust to the satellite. Again, we know that that is not true. If you've been on this planet for long, you'll know that satellites are not constantly firing rockets to keep their circular orbits. They're just sitting out there floating at a speed that keeps on moving. Okay. All right. So D, the centripetal force of the satellite is balanced by the gravitational force. See, this question implies that there is more than one force acting. Okay. What did I say? There is not more than one force acting. There is only one force. It is the weight force, the gravity force that is acting. So D is again just contradicting everything that you've been taught. Okay, so look at B. The orbit of the satellite has a fixed radius. Well, it says a satellite is orbiting a planet at a constant speed, which means that it is not in an elliptical orbit, it's in a circular orbit for its speed to not be changing. So if you had a look at the lecture online that I did and saw Kepler's laws and the elliptical orbits, you see in the elliptical orbits, objects speed up towards the gravity mass and slow down as they get away from it, and only to speed up again when they approach. So if this object has a constant speed, then the orbit must be circular. So if it's circular, it's got a fixed radius, it's not changing in any way. Awesome. All right, let's skip down to question 41. Question 41, a mass. This is a very common question. It requires you to kind of have a working knowledge of how the inverse squared law affects the sort of gravitational force that an object feels from from a larger mass, like a planet or a moon. So in this case, they give us a 20 kilogram mass is taken to a distance of 10 Earth radii from the center of the Earth. Okay, so 10 Earth radii from the very middle is actually 9 from the surface, and that can be important depending on how the questions how the question is, you know, asked, basically. So, if we look at it, you need to keep in mind that if we've got the Earth, okay, and there's a point in the middle, now it has been moved, this 20 kilogram object has been moved from the middle of this planet to 10 Earth radii out. Okay, so this R is 10, is basically 10 times further than from the middle. Okay, now basically it's asking what effect does that have on the force that this object feels at that point. Now, you know, at the very center of the Earth, it would feel nothing. Okay, it's 0. At the surface, it is 1 Earth radii away from the center. Okay, and at 1 Earth radii from the center, it feels 9.8. It feels a force of 9.8 times 20 kilograms. Okay, so 9.8 times 20 kilograms is what it feels at 1 Earth radii. At 10 Earth radii, it will feel the inverse squared. Inverse basically means to divide, okay? So you're going to flip over that 10 and square it. So you don't divide by 10, you divide by the inverse squared, which is by 10 squared. So what you're really looking at is force varies with the inverse square of the radius, and since it's 10 times further out from the middle than the original one was, which was only 1 times out, then you take that 9.8 times 20 and divide it by 100, and that gives you the force that this object feels at 10 Earth radii from the center of the Earth, okay, as 1.96 newtons, which would then significant figure it down to 2 newtons, okay? Now, there are questions that say 10 times from the surface of the planet, and in that case, it takes you from 1 Earth radii to 11 Earth radii. So I remember doing a question like that many years ago, and so the rule is still the same. But if you just remember that the question may be stated as in from the surface of the Earth rather than from the center of the Earth, then you just have to keep in mind that you are now 11 Earth radii out from the center, which would means the inverse squared is 1 over 11 squared. So you divide it by 121, not by 100. Okay, I just remember that one from ages ago. All right. If we want to calculate the orbital speed in question 42, we're basically going to just be using, if I move the page, yep, okay, we're just going to be using, let's see, you've got Gm, so that's big M on R squared, which is acceleration, and we're going to equate that with the acceleration of the body of the satellite, which is V squared on R. Now, you'll remember we did this with F equals Gmm on R squared, and A is equal to V squared M on R, because they're both versions of F equals ma, but in this treatment of it, we've kind of skipped putting the little m's in, which we cancel out anyway. It gives you this result anyway. This is something that should be on your help sheet, okay? So I see a hint there. So when you solve this arrangement for V, you end up with V is equal to the square root of big G, big M on R, okay? The only landmine buried in this question is basically this is a 200 kilogram satellite. That makes no difference to its orbital speed. It's just given it to you as a bit of a red herring. And it's placed at an altitude of 300 kilometers, which is 300,000 meters, which is 300,000 plus 6,400,000 meters to give you what the r in this equation actually is. Okay, so that is really 6,700,000 meters. So 6,700,000 meters is what your r is. And of course, no matter how many times I say it, there will be at least one person in a SAC or an exam that just ignores the word altitude. It's very frustrating. So chuck your values in there, and this question is basically 3 marks for basically turning up. All right, a very easy question. Okay, now what's next? Is there anything interesting here? Calculate the orbital period of the satellite. Again, we have this, v equals 2 pi r on t. Just rearrange it. Again, help sheet stuff. No reason to ever get anything like this wrong. Just use the values that you're given and fit them into the formulas that are populating your sheet. Okay, so that's an easy one as well. Calculate the gravitational acceleration experienced by the satellite in orbit. So the it's just them trying to be like clever with their wording. Oh, did you see that? Okay, calculate the gravitational accelerations, the gravitational field strength. It's G. They just want G. Okay, so bang, G equals big G, big M on R squared. All right, so let's calculate this. All right, and calculate an amateur astronomer for the next question on Earth measures the orbital period of the International Space Station in the night sky as 94.7 minutes. Calculate the altitude of the International Space Station based on the orbital period of 94.7 minutes. Okay, so again, link this to the radius and period of the satellite. So to figure out the altitude, you first need to find r. Okay, so you can do that by equating RSS. Okay, so that is the radius of the space station over the period squared of the space station, and using the values from earlier, you can then calculate, well, you could just equate it to what you have on your help sheet, which was GM of 4 pi squared. So you can do it that way as well. All right, but and solve for r. So once you've solved for r, take away the radius of the Earth, and that will give you the altitude. Okay, so that's another pretty easy question. Okay, what else have we got? Okay, this one was kind of interesting. This question kind of alludes to the kinds of stuff that came in with the new study design. And with the new study design, they've tried to add a lot more sort of data analysis or data treatment to make it more sciencey. Okay, so here it says, okay, Henry Cavendish first measured the mass of the Earth by initially measuring the gravitational force between masses of lead at various distances. Consider the data below that represents the force between two masses of 20 kilograms and 50 kilograms at various distances. Now you can see you've got R there, so these are the distances between the objects. So you can see 0.2 meters, 0.25 meters, 0.3 meters, and so on. Okay, and the force that exists, you can see 1.7. This is 1.7 newtons, but 1.7 by 10 to the negative 6, because obviously for such small masses, the force of attraction is incredibly small. Okay, so what the question goes on, what formula will allow a straight line graph to be created from this idea? Okay, so this is very much a mathsy question. Okay, so the force is calculated by what we have given here, GMM squared on R squared. okay? This tells us that the force varies with the inverse square of r, okay? So what formula will allow a straight line graph to be created from this data? It is F equals GMM on r squared, all right? In the blank row in the table above, complete values that will create a straight line. So to create the straight line, you have to basically take the curve out of it by actually doing the calculation of the 1 over r squared. So you take your r and square and take the reciprocal, and you end up with the values 25, 16, 11.1, and 8.16. Now with your methods and you know, with your methods knowledge and all the maths that you've done, you should, you know, hopefully see that this is how you would take your graph and it would turn what is ordinarily a curvy graph into a straight line graph. Okay, so then they want you to go off and graph it, which is graphing force up against 1 over r squared, which is to give you that straight line graph on this graph paper, and you can go through the values that they've specified on the axes are going up in radii of, well, the reciprocal square of radii, 5, 10, 15, 20, 25 to fit these values in, okay, and the force is 0.5 newtons, 1.00 newtons, and over here 1.5 newtons, and 2 newtons here, 2.00 newtons there. So, but this is, now don't forget, if you're going to label these axes and get all of the marks in the question, if you've gotten this far in a question like this, you can't just write force, you've got to write force, and in brackets, don't forget to chuck in times 10 to the negative 6, because that's what they want to see, that you are aware of the scales on the graphs, okay? It's really important that you put all the detail in there. And then you end up with the line that kind of does this up here somewhere, all right? I don't want to waste time plotting dots, okay? Then it goes on and says, calculate the universal gravitational constant from your graph showing all working. So, F, as you can see here, F is equal to GMM on R squared. Okay, so what they've gone here is they've basically gone through and said that, okay, what is, you need to try and kind of get to the point where you realize that this this gradient here is the rise over the run, and so the gravitational constant that links F to 1 over r squared is G itself, okay? So the rise over run, so GMM on r squared is F, okay? So that's your rise, and your run is this calculation, which is 1 over r squared, okay? So that's your rise, and your run is the value along the horizontal axis, which is 1 over r squared. So if you then go and try and create your rise over run, all right, what you end up with is GMM on r squared over 1 over r squared, okay? So what does that leave you with when you do a little bit of flipping and multiplying? The r squareds cancel out, and it gives you a rise over run, which is equal to G big M. Okay, so that is what, that is your rise over run calculation. So you need to now equate this by going GMM is equal to your rise over run, which gives you, now you have all of the values for this. Your GMM is your gravitational constant, which is 6 point, can you see this? Yeah, which is 6.67 times 10 to the negative 11 multiplied by both masses, 50 kilograms times 20 kilograms is equal to the rise over run, which is a calculation of you just going rise over run, the typical rise over run for a straight line, which, you know, the whole y2 take away y1 over x2 take away x1, that calculation based on your straight line here, and just using the values that are given, 1.7 take away 0.54 over, that would be your rise, 25 take away 8.16, that's your run. And that is, oh, okay, yeah, so I've made a little bit of a mistake here. You do all of this, but the whole object of this is to find G from actual data. So you would not actually use, can you see this? Like, I'm gonna use my little whiteout tape there. What you're supposed to have done, obviously, sorry, is left that as G, big G, and solved for it to prove that these values give you an answer that is close to the accepted value of G. That's all it is. Okay, so you complete that calculation, you get something that's pretty close to G. Okay, all right. So that's a pretty heavy question. All right, here's another question, sort of 50, 51, 52. They're also a really good question that tries to link stuff you've already learned when it comes to like momentum, change in velocity, acceleration, to the motion of planets and objects around planets. That's what they're trying to do with these questions. So here you've got space agencies like NASA use planets to speed up or slow down space probes and to redirect the probes to new trajectories. This is often called slingshotting. Okay, now consider Voyager 2, when in 1977 it passed Jupiter on its way to the outer planets and eventually to outer space. And Voyager 2 did leave. It's that satellite that had the gold records and gold discs on them, just in case anybody out there found them. So they did this. They did this like 3 or 4 times on the way out, and each time they sped them up. They ended up leaving way faster than they actually left the Earth. By doing this really works. And it was, you know, and again they used Newton's equations to do all of these calculations and make it all happen. It was pretty amazing. Anyway, so it approached this object. Let's say this object, this particular spaceship, approached Jupiter at 10 kilometers per second. Change direction through 90 degrees. That's important. And left at 20 kilometers per second, as illustrated in the diagram. Okay, the mass of Jupiter is 1.9 by 10 to the 27 kilograms. Okay, so draw a suitable diagram showing the change in momentum of Voyager to be calculated. All right, now to calculate the change in momentum, you need to get its change in velocity. Change in velocity does not change, or the way you do it doesn't change in any way, no matter what chapter you're doing. So final velocity, take away initial velocity. And this is why I said that this turn through 90 degrees, which I don't believe it actually was a turn through 90 degrees, because that would have been too perfect, but that what's happened here is the final velocity of the probe was 20 kilometers per second. Can you see it? Out here in this direction. So I'm going to draw that vector because that's the final. It's final takeaway initial. So the final stays how it is, and that's 20 kilometers per second. But the initial, it's take away the initial. So if the initial was coming in hot like this, then to take it away, we've got to flip it around and then join it head to tail, and keep in mind, so it's flipped around, so final takeaway initial. Doesn't matter if I add it here or put it over here, you end up with the same thing, okay? So you can't get that wrong. Just follow the rules of head to tail, okay? So there's final takeaway initial, and it happens, as it says, at 90 degrees. This allows us to actually do the calculation using something nice and simple like Pythagoras. So our our change in velocity is this vector right here, Okay, that's our change in velocity, delta V. All right, beautiful. Okay, show that the magnitude of the change in momentum is about 1.8 by 10 to the 7 kilograms meters per second. And the only way you can do that is by finding the actual magnitude of the change in velocity and multiplying it by the mass, which the mass of the space probe, which is given 820 kilograms. All right, so you sprinkle a little Pythagoras on this here, and you end up with 20 squared, take away 10 squared, square rooted, gives us, well, fast forward, gives us 22.36 kilometers per second. All right, now 22.36 kilometers per second is really 22,360 meters per second. See how I didn't forget to do that? That's right. Okay, that is our change in velocity. So its change in momentum is m delta v, which in this case it's an 820 kilogram spaceship multiplied by 22,360 meters per second. That gives us 1.8 times 10 to the 7 kilograms meters per second as our change in momentum. Then it moves on and says, okay, the time to pass Jupiter was 15 hours. Calculate the magnitude of the average force on the probe. Now, calculating the magnitude of the average force on the probe, you can see that this has really transitioned into very much a momentum type question. So, maybe you hark back to your momentum section in your help sheet, and you'll notice this nifty little formula that you have sitting there waiting for you. F delta T is equal to m delta V, and if you remember, this F is often referred to as the average force experienced by an object as it changes its momentum over a given time. So they've given you a time, 15 hours, you've just figured out the change in momentum, and they've asked for the average force. So, seriously, what more do you need? Okay, so the average force is just going to be F is equal to the change in momentum over how long it took to do it. Change in momentum you've already got from the previous question, and divide that by how long it took, which is 15 hours, which is 15 times 60 times 60. Because we do this does rely on several other values, okay, that are in meters per second and newtons and all that stuff, which means you can't just chuck 15 hours in there and expect the right answer. All right, you end up with something approximating 340 newtons of force is what was experienced over the slingshot period. Nice. All right, the question goes on. 53. Calculate magnitude of the change in momentum of Jupiter. Well, I know what you're all thinking. Isn't momentum always conserved? So whatever change in momentum occurred for the satellite also occurred for Jupiter. Well, I'm glad you were thinking that, because that is absolutely correct. So conservation of momentum, whatever the change in momentum was for the satellite, Jupiter experienced the same. And again, they're very careful, kilograms, meters per second. They're very careful to chuck in the word magnitude over and over again, because it takes away the necessity for you to actually go calculating angles and all that sort of thing, because obviously these momentums are dependent on direction, and so they use the word magnitude. You've got to learn to see that word magnitude to make sure that if you don't see the word magnitude, that you do need to include a direction. Okay, so what effect will this interaction have on the orbit of Jupiter around the Sun, and justify your answer? Well, in this, basically, to calculate the change in velocity, or that is caused, or the acceleration of Jupiter as this satellite moves around it, you would say, well, okay, we know that the change in momentum of Jupiter is this, okay, and we also know that, so that is, we also know that this is equated to mass by delta V, all right, so change in velocity. So if we want to figure out what the change in velocity of Jupiter is during this interaction, what you find is when you factor in the mass of Jupiter and solve for the change in velocity, you end up with some ridiculously tiny 9.7 by 10 to the negative 21 meters per second is the change in Jupiter's velocity, which is the effect that having the satellite slingshot around it had on it. It is so small that it's immeasurable, it's negligible. Okay. Now I found this particular question, number 55, quite interesting because I actually didn't know this until I read it. And so, how might NASA slow down a probe by passing a planet? We all know that the slingshot is really about speeding things up, so you don't have to wait so long to get anywhere out there since everything's so far apart. But never have I actually stopped to think, can you actually slow down a probe using the same kind of maneuver? And apparently, yeah, you can. So what it comes down to is that if you want to slingshot around Jupiter and speed up, then you have to approach Jupiter from an angle that coincides with the direction that Jupiter's already going in. So if you hit it from the side of, hit that little imaginary window from the side of Jupiter, which then takes your velocity and adds it to the velocity that Jupiter already has as it's moving through space, that is where you're picking up your extra velocity, okay? So it then makes sense that if you wanted to slow down, you would approach Jupiter from the other side, so that as Jupiter was moving, you would slingshot around Jupiter in a way that was opposite to its direction of motion, and hence the interaction would then slow you down rather than speed you up. And that was the actual answer to that question. I'm not going to write that. You've got to, it's all detailed in the solutions. Anyway, all right, so example 56. It's just a basic question. You can, if you're not able to figure it out yourself, you'll follow that one easily from the solutions that are provided. All right, we're going to now skip down to question 78. There's a lot of questions up to here between the last question that I did and this one, where there's just lots and lots of algebra fun, basically. There's nothing I can really teach you by explaining. You'll see, because it's very algebraic, a lot of, what is the ratio of this value to that value? You'll see that it's nothing that I can really do other than just go over exactly what they've done, which you can do for yourself. I did want to, I got down to this question here, example 78, because it does hark back to that part of the lecture that I did earlier about Kepler's laws and elliptical orbits. So these do come up, questions like these do come up occasionally, so it's good to have a sort of good feel for it, so you can see, and this is why I also showed you that animation describing the object moving in its orbit and speeding up around the sun, or whatever the planet was, whatever the object was, and slowing right down out towards the other side of its motion. Okay, so here, figure shows the orbit of a comet around the sun. Describe how the speed and the total energy of the comet vary as it moves around its orbit from point X to point Y. So, it says in bold, speed and total energy, okay? You do need to make reference to both of those things. It is worth 2 marks. If you want both marks, they're really easy to get. Okay, the total, you can start by saying that the total energy of the comet never changes. Okay, what does change is the relative amounts of kinetic energy and gravitational potential energy that the comet has at different parts in its orbit. Okay, so when it is very close to the sun, it has its maximum kinetic energy as it is moving the most quick, the fastest. It's moving with the highest velocity at that point, which means it has a minimum of gravitational potential energy. When it is moving, and you can use the reference points, that's why they put them in there. There's a reference points X and Y. So when you say, as the comet approaches point Y, it is moving at its slowest velocity and hence has the least amount of kinetic energy and the greatest amount of gravitational potential energy. And you can even make a second state again, thus the total energy of the system or the comet never changes. All right, so that's a really important one. A very easy explained question because it wants you to reference two very clear aspects of orbital motion around in an ellipse around an object, around a star. Okay, all right. So now we go down to the kind of very last or second last question. Okay, number 79. Halley's Comet last passed by Earth in 1986. The path of this comet is elliptical. Part of this ellipse is shown below with P, Q, and R representing 3 points along the path. You can see this, right? There's the diagram. You should be looking at your own version of it. Okay. Calculate the magnitude of the gravitational field strength at point P due to the sun. Okay, now it gives you everything you need there. That's a really easy. The gravitational field strength, G is equal to G big M on R squared. So that's the gravitational field in that, at that area, at that distance from the sun. Okay, so you chuck the values in that are given and there you go. You've got a nice answer there. When you get down to question 80, okay, in question 80, there is something to kind of look out for because there are a couple of versions of this kind of question that can catch you out. Okay, so let's have a look at this little graph here. Okay, the diagram below shows a graph of the gravitational force that the sun exerts on Halley's Comet as a function of the distance of the comet from the sun. Now, notice this unit here. This is force, and it's given in gravitational force in newtons. Okay, you can see it's in times 10 to the 9, all right, newtons. All right, now there is another version of this graph which occasionally appears. Sometimes this graph will appear with a newtons per kilogram attached to it, okay? So that's a nice little snare trap left out in the forest for you, okay? Basically what that does is it means that any kind of energy calculations you make only give you values that are per kilogram. Okay, so let's say it's a satellite and it weighs 200 kilograms and they've given you force on the satellite of newtons per kilogram. Any calculation of the total energy of that 200 kilogram satellite needs to include you going, okay, whatever that energy was, that's the number of joules per kilogram, so that's 200 kilograms, multiplied by 200, and there's the energy contained in that object, all right? So, in this case though, there is no per kilogram, so you don't need to include that calculation. All right, you don't need to actually do it because what they've done here is they've already included it in these values here. All right, so they've already taken into account Halley's Comet's mass. All right, so when you're doing things like when you're calculating its orbital period, its radius, and its speed, none of that matters when it comes to its mass. All right, the mass doesn't matter how heavy it is or sorry, how massive it is to those values. But when you're doing calculations around energy, then it does matter. Okay, so keep that in mind because as kinetic energy, mv squared on 2, gravitational potential energy, GMH. Okay. They both involve the mass of the object. You know, you want to be Do you want to be hit by a feather or a bowling ball? Okay, so yeah, how much energy is imparted does change on how massive the object is. Okay, so what we do here is we need to figure out, it says, estimate the increase in kinetic energy of the comet as it travels from point Q from the sun to point R. So point Q to point R. Look at point Q, look at point R and the direction of travel. So it's going to change its energy, okay, by that amount, okay? So from 3 by 10 to the 11 meters away from the sun to 1 by 10 to the 11 meters from the sun. So you go over to the graph and these always work the same, okay? Once you've done a couple of these questions, you'll wonder what you were worried about, okay? So you can see it's going to shift its position from here, or well, actually from here, from 3 to 1, okay, as it approaches, all right? So it's all of this area under the graph, okay? So what you need to do, not all that, just to here, okay? So you want this area only, okay? Now, estimate the increase in kinetic energy of the comet. So this is the change in energy that it experiences, whether it's going up or down. Now, if it's coming towards the planet, it's going to be getting quicker towards the sun. So it's going to be getting quicker, which means its kinetic energy is going to go up by this amount. So what you need to do is figure out, well, what's one of these squares worth? All right. So to figure out what one of those squares is worth, it's, well, it is 1 by 10 to 11 wide by 2 by 10 to the 9 high. So just multiply, grab yourself one square and figure out how big it is. 1 by 10 to the 11 times 2 by 10 to the 9 gives us 2 by 10 to the 20 joules. Okay, so it's giving us what? Huge amount of energy here. All right, now that is how much one square is worth. All right, so what is its change in kinetic energy will be whatever it loses in gravitational potential. All right, so how do you count squares? Excellent question, kids. A whole square inside the shaded area counts as 1. Okay, obviously there's 1. If I have nearly a whole square chucked in, I'm going to count that as a whole square, so that's 2. All right, down here this is nearly a whole square, there's a bit of it cut off there, that's going to count as 3. Okay, I'm not going to count this or this at all, okay, because they are less than half of the square shaded. 1, 2, 3, and I'm going to count this one as well because more than half of it has been included inside the graph. So what I've got here is a nice sort of guesstimation method for counting squares. I have got 2 by 10 to the 20 joules per square. I have 4 squares that I can count, so times 4. The answer, 8 by 10 to the 20 joules, which is like, sounds like a crap load to me, but it's the answer. All right, question 8, that was example 80. Hope that was as much fun for you as it was for me, and look forward to catching you on YouTube soon. Bye for now.